All right, welcome. Today we're doing a full doctoral level breakdown of influenza. We're going to get into the virology, how it's diagnosed, and how we actually manage one of the most clever and persistent viruses out there.
So here's our game plan. We'll start with the virus itself, then move into diagnosis and treatment, touch on the specifics for kids, and then zoom out to public health and the big questions we're still facing.
Okay, first up, let's get to know our adversary. To really get a handle on influenza, you've got to start with the virus itself and what it does to the human body.
So influenza viruses are part of a family called Orthomyxovertidae. Now, the most important thing to know about them, the real key, is that their genome, their genetic code, is in pieces. It's a segmented RNA genome. And that's not just some trivia for a textbook. That segmentation is its superpower. It lets different flu strains mix and match their genes, kind of like trading cards. This process, called reassortment, is the engine that drives its crazy fast evolution. It's why we're always focused on types A and B. They're the ones that use this trick to cause all the trouble.
And you can see that evolution right here. This timeline shows how different strains have dominated over the years. You've got two things happening. First, there's antigenic drift. Those are the small, yearly changes that mean you need a new flu shot every season. It's like the virus is just tweaking its disguise. But then you have antigenic shift. That's the big one. That's when a whole new player, like H2N2, storms the stage and kicks the old one out. It's a total genetic reset, and it's what can cause a pandemic, just like we saw in 2009 with the new H1N1.
And when it hits you, it hits hard. This is definitely not a common cold. After just a day or three, it comes on suddenly, like a light switch. The classic sign of influenza is that trifecta of a high fever, really intense muscle aches, that's the myalgia, and a headache that just won't quit. You feel like you've been hit by a truck, and that's how you know it's probably the flu.
Okay, so your patient feels like they've been run over. You suspect the flu. How do you actually prove it? Well, getting the right answers starts way before the sample ever gets near a machine.
This part is absolutely critical. You can have the most advanced lab in the world, but it's garbage in, garbage out. You've got to get a good swab, get it into the right transport liquid immediately, keep it cold, and get it to the lab fast. That viral RNA is fragile stuff. If you mess up any of these steps, the sample's no good, and the test is useless before it even begins.
So once the lab gets a good sample, there are a couple of ways to go. You have the rapid antigen tests. They're fast, you can get a result right there in the clinic, but they're not super sensitive, so you can get false negatives. Then you have the gold standard, PCR. Think of it like a genetic photocopier. It can find even the tiniest shred of viral RNA and make millions of copies until it's easy to detect. That's why for a definitive, no doubt about it diagnosis, PCR is the only way to go.
Right, so we have a confirmed positive case. The question is, what are we going to do about it? Let's get into therapeutics, what drugs we have, and how we use them.
This is our antiviral arsenal. The two main workhorses today are the neuraminidase and endonuclease inhibitors. Neuraminidase inhibitors work like bouncers at a club. They stop new virus particles from being able to leave an infected cell. Endonuclease inhibitors work earlier, sabotaging the virus's ability to replicate itself in the first place, and as you can see, they both work on Influenza A and B. The older drugs, the M2 blockers, they're basically useless now for seasonal flu because the virus evolved widespread resistance, a real cautionary tale.
So let's make this real. Let's walk through a standard case. You have an adult patient sick enough with confirmed influenza to be admitted to the hospital. The clock is ticking. What is the standard of care?
Here's the play. Oseltamivir. The dose is 75 milligrams, twice a day for 5 days. And the most crucial part is starting it early. The data is crystal clear on this. The sooner you get this medication on board, the more you shorten the hospital stay. And, most importantly, reduce the chance that the patient will die.
Okay, we've been deep in some pretty heavy clinical details, so it's time for a quick palate cleanser. This one's for the microbiologist listening. Why did the bacterium break up with the virus? Because they had no chemistry, and the virus was always negative. Yeah, okay, moving on.
But seriously, what works for a standard adult patient is not a one-size-fits-all solution. When we're talking about kids, we have to adjust our approach. They have a completely different set of risks.
And here is the single most important takeaway for kids.
This isn't a suggestion, it's a clinical mandate. If a child under 2 years old gets diagnosed with influenza, they should always be treated with antivirals. No debate. Their immune systems are still developing, their airways are much smaller, they're just so much more vulnerable to severe complications. We don't wait and see, we treat.
All right, we've been focused on treating the individual. Let's pull the camera back now and look at the big picture. How do we stop this thing from spreading and keep an eye on it at a population level?
This is where the detective work comes in. Public health surveillance isn't passive, it's an active hunt. And these reporting rules are tripwires. Anytime an animal flu jumps to a person, or a lab finds a weird virus they can't identify, or we think our drugs might be failing, an alarm bell has to be rung immediately. This is our early warning system for the next big threat.
And all of this is built on a foundation of infection control. It's a spectrum, really. It starts with the simple things we should all be doing: washing hands, covering coughs. And it goes all the way up to institutional policies, like mandatory vaccination for healthcare workers and handling these viruses only in high-level biosafety labs. Every layer matters.
So, let's wrap this up by looking at what happens when things go really wrong, and the huge questions that researchers are still trying to answer.
You know, the flu itself is bad enough, but it's often what comes after that's truly dangerous. The virus damages the lungs, basically rolling out the welcome mat for other invaders. The most common complication is a secondary bacterial pneumonia. It's a classic 1-2 punch. And in the ICU, for the sickest patients, we also have to worry about opportunistic fungi like aspergillus taking hold.
And this, right here, this is the final multi-billion-dollar question. Influenza is a master of this game. It's perfected the art of jumping from animals to humans and then spreading like wildfire. So many other viruses try and fail. What is influenza's secret? What is that specific biological key that unlocks the door to a full-blown human pandemic? Because finding that key is probably our best hope of preventing the next